Now we will begin our explanation of Thermistor Workshop Basics, Part 2, Temperature Sensor Circuit Creation, and use examples. First, we will explain the specifications of the thermistor we will use to create the temperature sensor circuit. At the widely used temperature of 25 degrees Celsius, a thermistor can have a resistance value of 10 kΩ to 100 kΩ. Using a resistance value of 10 kΩ is common in automotive applications, whereas in applications such as smartphones, a value of 100 kΩ might be used to reduce power consumption. In this case, we will use a size 1005 resistor designed for automotive use with a resistance value of 10 kΩ and resistance tolerance of plus or minus 1% to create our temperature sensor circuit. This is a diagram of the temperature sensor circuit we will create. We connect a 6.2 kΩ resistor R1 and an NTC thermistor in series to the 3V power supply, which is then connected to ground. The basis for selecting a 6.2 kΩ resistor as R1 is explained in Part 3 Design Support in SimSurfing. For the ADC, we will use pin PA4 on a commercially available evaluation board populated with a STM32L152 microcontroller manufactured by STMicro. For the power supply, we will use the 3V and GND pins on the evaluation board. The components we will use are these three items. The first is a 1005 thermistor chip. We will mount this on the board. Next is a 0.1F leaded capacitor marked 104, produced by Murata Manufacturing. Then there is a 6.2 kΩ leaded resistor with a blue-red-red-gold marking. We wire these components together on a breadboard to create the circuit. This wiring is also used to connect the breadboard to the evaluation board. The breadboard makes it simple to create circuits by connecting leaded components to the holes in the board. If you look at the back, you can see that the positions of the conductive holes are connected by pieces of metal. Vertical lines 1 to 30 have connections between the upper and lower sections, and the red and black lines are horizontal conductive lines. The red lines are separate, but on this board they are connected by shorting pins, creating conductivity between them. Now let's create the circuit. First, we'll use jumper wires and IC clips to make 3V and GND lines on the breadboard. We'll use IC clips to connect to the 3V and GND pins on the evaluation board. We connect the other IC clips to the jumper wires. We connect the other ends of the jumper wires to the red and black lines on the breadboard. Here, we have created the 3V and GND lines on the breadboard. Next, we will connect R1 and the thermistor in series. We connect the number 9 lower section line to the thermistor and the other end to the GND line. Then we connect the same number 9 lower section line to the 6.2 kΩ resistor and the other end to the 3V line. We connect the bypass capacitor between the number 9 lower section and GND lines. Finally, we connect a jumper wire to the number 9 lower section line and secure the other end with an IC clip. We connect the other IC clip to PA4 on the evaluation board. This completes the circuit. The expression showing the relationship between temperature and voltage described in Part 1, NTC Thermistors and temperature sensor circuits, is shown here. We will explain how to derive relational expressions in Part 3, Design Support in SimSurfing. Now we will input the temperature and voltage relational expression into the microcontroller and check to see if the temperature sensor circuit connected to the thermistor operates as intended. The STM32L152 Discovery Evaluation Board we are using is equipped with a liquid crystal display, and we will output the temperature to this display. Now we will write the program to the microcontroller. The numeric value of the 2 digits after the decimal point is outputted to the display to show the room temperature. Next, I will touch the thermistor with my finger and confirm that the temperature rises. As you can see, the temperature rose. By using the simple electric circuit and writing the temperature and voltage relational expression to the IC, we were able to create a temperature sensor circuit that shows the temperature of the thermistor. Next, we will present 2 examples for the temperature sensor circuit. The first is an alert circuit. We will set the 2 alert temperatures of 30 degrees Celsius or above shown in the table. This is a sounder circuit that produces a warning tone. We will connect a 330 ohms resistor to prevent inrush current and a 2 kHz sounder from Murata manufacturing in series to pin PA12 of the microcontroller and then make a connection to ground. This type of sounder is used to generate warning tones on sliding doors and the like. To generate an alert consisting of a flashing LED, we will use the LED on the microcontroller evaluation board. We will use these 3 components to create the alert circuit: a 2 kHz sounder, a 330 ohms resistor, and wires for use with the breadboard. Now let's create the sound circuit. First, we'll use a wire to short the G&D line and the number 28 lower section line. We then connect the number 28 lower section line to one end of the sounder and the other end to the number 28 upper section line. Next, we connect one end of the 330 ohms resistor to the number 28 upper section line and the other end to the number 29 upper section line. We connect a jumper wire to the number 29 up section and use an IC clip to connect to PA12 on the evaluation board, completing the sound circuit. Now let's check the operation of the alert circuit. We have confirmed that when the temperature exceeds 30 degrees Celsius, a warning tone sounds and the LED flashes faster. When the temperature is 30 degrees Celsius or higher, a 2 kHz square wave signal is outputted to the IC, and the program written to the microcontroller causes the interval at which the LED flashes to change from 0.5 seconds to 0.1 seconds. This was a simple example of an alarm and alert circuits that responds to temperature. These circuits are incorporated into many products. Next, we will describe the use of temperature sensing for temperature compensation. Temperature compensation means to suppress changes due to variation in temperature on components whose characteristics change with temperature. Characteristics such as the output strength of a laser or the sensitivity of an image sensor are affected by temperature, but stable operation can be obtained by making adjustments to match the temperature. The oscillating frequency of a crystal unit also changes with the temperature, so it is necessary to adjust the frequency for applications requiring frequency accuracy. Here we will look at frequency compensation for crystal units. An oscillation circuit employing a crystal unit looks like this. CL1 and CL2 are capacitors used to make fine adjustments to the frequency. For CL2 in this temperature compensation demo, we will use a variable capacitor produced by Murata manufacturing. A variable capacitor is a component with 4 pins. Altering the voltage applied to G&D and V-tune changes the capacitance between port 1 and port 2. By using this variable capacitor as CL2, we can adjust the capacitance to cancel out the change in frequency of the crystal unit due to temperature variation, thereby correcting the oscillation frequency. Now let's check the temperature compensation of the crystal unit using a spectrum analyzer. The peak of the waveform is the oscillation frequency. One division on the horizontal axis represents 20 Hz. The crystal unit has an output frequency of 24 MHz, so one division H is equivalent to about 0.8 ppm. First, we will take a look at the thermal dependence of the crystal unit's frequency when no frequency compensation is applied. We can see that when the temperature rises from room temperature to 40 degrees Celsius, the frequency changes by about 60 Hz, or approximately 2.4 ppm. Next, let's observe the thermal dependence of the crystal unit's frequency when temperature compensation is applied. We have input a program that applies temperature compensation every 0.5 seconds. As you can see, the oscillation frequency is being adjusted every 0.5 seconds. This shows how incorporating a temperature sensor circuit allows us to apply temperature compensation to the frequency of the crystal unit. In Thermistor Workshop Basics, Part 2, Temperature Sensor Circuit Creation and Use Examples, we described the creation of a temperature sensor circuit and presented examples. We hope you gained an understanding of how you can perform temperature measurement using a very simple circuit and some of the uses such a circuit can be applied to. Thank you for your attention.